Welcome, dear students, for continuation of the lecture on liquid drop model. I would like to take off from where I left in my previous lecture. If you recollect, we had the expression for the binding energy, and we saw that the binding energy expression has three contributions. One is the volume contribution, surface contribution. Since they're charged particles, you have the Coulomb contribution also. So it's a combination of all this which will then determine the binding energy, or good or how bad the nucleons are bound within the nucleus. The objective, let me again tell you, is we want an expression for B. From this expression of B, I want to plot the famous B by A versus A graph, which all of you know, which we know what is the shape of the graph, and I want to reproduce this graph using liquid drop model. So this is the graph. I think there are a few from this line. So this is your B by A on the y-axis plotted against A. So if we have an expression of A, B, I can take B by A versus A graph and see whether I'm able to get this shape. This is going to be the first test of the model, and after that we are going to be testing the model whether it's able to predict various nuclear phenomena or not. This is called mass formula. So basically we are trying to get the mass formula. You know that mass and binding energy are connected, because binding energy is nothing but finally delta m square. Delta m is the difference between the individual masses of the nucleons, summation of them, minus the mass of the nucleus. You know that when the individual nucleons they come together and form a nucleus, their mass decreases. So that decrease in mass is delta m multiplied by c square is what I'm going to get B. So let's see how we proceed. So we are trying to get an expression for B. It has three contributions: ABA minus ASC raised to 2 by 3 minus AC z square upon A raised to 2 by 3. Actually, the z square is, in some books you'll find this to be z into z minus 1. This is the actual term, but I can approximate it to be z square. So that's what I've done here. So don't get worried. Even if you write z into z minus 1, it's okay. Or if you write z square, then also it's okay. Right? Now from this, I take A on this side. So I get B by A expression. AB term, this is the AC term. I mean AS term, surface term, and this is the AC term. Okay? This is what I get. Now let's plot this individual term. So what I'm trying to do now is I'm going to be taking A on the x-axis and B by A on the y-axis and trying to plot individual terms. For example, first I'll draw AB. AB is a constant, so this graph will be constant like this. Then I'll plot this term, then this term, and then take the summation of all three and see whether I'm able to get the graph of P by A versus A or not. This has been shown here in this diagram. You can see that this is the volume term. It's a constant. It is not dependent on the atomic number. Okay, atomic mass. Now here you can see this here 0. This is a plus 5. This is a minus 5. You can see that the Coulomb term is on the negative side because it has got a negative contribution. You have minus AC, you got minus AS. So that's why it is shown this, the surface term. You can take an Excel sheet what you can do is you can take an Excel sheet. You can have different values of A, and then you can generate BS for different year, and you can take BC. BA, this AC, this term AB, AS, and AC are constant. Right now, you can take whatever value you want, or the constants are given in the book. I will be talking about this constant later on. This constants, and then what you do is you can take an Excel sheet and you can generate BS term, BC term, AB term is a constant. So if you just add all of them, and then you will get this type of a graph for B by A. Consider the graph has been reproduced. So this is a big triumph of the liquid drop model. The shape has been reproduced. But dear students, the shape has been reproduced only partially, because there are certain, as you can see, there are certain peaks here which it could not explain. So that peaks are not there. Those unusual peaks are not there at the lower A. And as you can see, other than that, the shape looks to be fine. So at the outset, it seems that everything is okay. The graph has been reproduced. So this is a great expression. AVA minus AS AC. Right now, forget about this. I will talk about this later. So these are the terms for the binding energy: volume term, surface term, and the Coulomb term. And the shape is produced, so this expression is okay. But later on we realize that as we keep testing it, there is some problem. Let's see what is the problem. Let us test equation 1, right? So this is your equation 1, the binding energy versus A. From this, okay, I have the expression for the binding energy. From this I get the expression for the mass. You can see that the mass M is equal to ZMP, the total mass of the protons plus total mass of the neutron, minus binding energy, is equal to the mass of the nucleus. Okay, so this is how you get. It's one and the same, because finally B is equal to, as I said, delta M C square. Now since I have binding energy expression, I get the mass expression. So this is what I do, and I write it as A minus Z, and then I simplify, so I get this expression. Okay, and then this is the mass expression. Now let us test this for isobar family. Now isobars are those set of nuclei, a family for which A is constant, a family for which all members have same A is same, but their Z is different. And if there are 10 members or 8 members or 5 members, amongst them one member is stable. For example, if you plot a graph like this again of Z, this is your Z of the isobar family, and this is your mass, you find that one of the isobar member is long lived compared to other members. If I have, let's say, 5 members, I'm just giving an example. This is number 3 member, this is the 4th member, this is the 5th member. And you can see that this third member here has the lowest Z. This is minimum. Now this is minimum. I'm sorry, not Z is minimum, mass is minimum. Yeah, you can see that the mass is minimum. Now you know that any element of mass is minimum is more stable. More the mass, more the instability. That's the reason why the higher nuclei, heavy nuclei are unstable. The lighter nuclei are more stable against radioactive decay. So you can see that lower the mass amongst these members, if you compare amongst these 5 members, the one which has got the least mass is going to be long lived. So basically at this point you also have dm. If you take the slope dm by dz, if you differentiate m with respect to z for constant a, it is 0. Okay, so that's what we're trying to do. Whether we take an isobar family, we'll differentiate m with respect to z and keeping a constant, and trying to see whether what is the value of Z that we are getting? Does it match with the actual value or not? Okay, there are many isobars families existing. So what we do is, first we differentiate is constant and equal to 0. So if you take, let us take a family whose A is 216. I differentiate, so this becomes this minus, if you take previous expression, you differentiate, this does not have any z, so this is differentiation is 0. This will have mn minus mp, this is no z term, this is no z term, this is got z square, so differentiation of z square is 2z. Like that I differentiate, put a is equal to 216, and I equate mn minus mp. There's hardly any difference, just an approximation, very little difference between mass of neutron and proton, so this I equated at 0 for convenience, nothing more. And I do the calculation. I know the value of AC. AC is a constant. They will ask me, how is the constant arrived at? This constant, you know what is arrived at? There are theoretical methods of doing it. Now coefficients, what happens is there's a graph like this. Now finally these coefficients are adjusted in such a way that you are able to get this shape. That's how this values are done. And there is also theoretical method of calculating the coefficient. We will see them later on. The coefficient is known here. For example, in this case, this coefficient AC's value is known, 0.6 MeV. So if you put this here, I get Z approximately equal to 3. So this result is very incorrect, because you cannot have A is equal to 216 and Z is equal to 3. So something is wrong here in this expression for the binding energy, which comprises of only three terms: the volume term, the surface term, and the Coulomb term. So we'll try to investigate and try to redefine the model. Now we will have to think beyond the liquid drop. So far we have thought nucleus as equated with liquid drop, and try to continue with the analogy, and whatever dynamics are involved in a liquid drop, we have tried to incorporate that in the nucleus, incorporating the volume term, the surface term, and then an additional Coulomb term. Now what we're going to do is, we are now going to introduce a term which will deviate from the analogy of liquid drop. Here we're going to be talking about quantization of energy levels. In nucleus, just as you've got quantization of energy levels in atom, where you have K shell, L shell, M shell, they can hold only definite number of electrons. And similarly, you have shell structure in the nucleus. And let's say, I'm just trying to represent this diagrammatically. Now you have first energy level. In first energy level, you have two neutrons, which I show by circle. Only I can have two neutrons, one with spin up, then obviously another will have to have spin down. Now here you can have two, sorry, there you can have two protons. Okay, this energy levels can have two protons. I just show protons by dotted circle. Now this has got spin up, one proton. Another has got spin down. If I have to fill the third neutron, then it has to be not in the same level, but then I'll have to go to the next level. Next level again, I can have one neutron with spin up and another with spin down. Similarly, I can have two protons here, one with spin up, another with spin down. So like that, you have energy levels that is trying to be introduced here. Now, moment you have energy levels, then the binding energy is going to be reduced, because now you're going to be having all nucleons not close by, but you have nucleons, some of them closer and some of them which are going to be in the higher energy levels. You know that electrons which are in the higher energy levels, if I have to compare with an atom, they're loosely bound and they can be easily removed. So let's see what happens because of that, this concept. Now what we're trying to do is, as you know that as z increases, for higher z, n is, sorry, for higher a, n is greater than z for higher a, right? As a increases, the number of neutrons is much more than number of protons. Okay, now let's see a scenario, what happens because of that. Right now we presume that whatever neutrons is present, it's because initially you had same number of neutrons and protons, and some of the protons got converted into neutrons. So in that case what happens, see, this is the first energy level, I've just shown it here. You can see two neutrons here, one with spin up, spin down, two protons, spin up, spin down. Next energy level, again one neutron with spin up, spin down, proton with spin up and spin down. Now just imagine that this four protons are getting converted into neutrons by a process called beta decay. We have seen that. The four protons get converted into neutrons. So what happens here, dear students? Just imagine that these four protons have got converted into neutrons. So these four protons will have to occupy energy levels higher than the one which is already occupied by the neutrons. So this one will occupy this energy level, while on the higher energy level go to a still further higher energy level. So basically you can see that each of the neutron, and let's imagine that the spacings are all equal. Epsilon is the spacing between each energy level. It's like this. This is the energy level. This is the energy level. And the spacing right now is equal. Right now I consider this to be epsilon. Later on we will see. We know that as the energy level increases, the spacing decreases. That we have seen in atom also. But right now we are not considering that. Now because of this, what is going to be happening to the binding energy expression? Let's see. I will take an example where I want to produce neutron excess of 8. So neutron excess of 8 means I want n minus z to be 8. Let's say I want n minus z to be 8. Whatever argument is holding true for this will also hold true for any of the general expression. Now, please pay attention. Earlier n and z were same and you had some binding energy. Now n is greater than z by 8. Then what will happen to the binding energy? Will the binding energy increase or the binding energy decrease? That is the argument we are trying to develop. Now to produce neutron excess of 8, okay, without changing a is constant. You know that in a beta decay process a does not change. So half n minus z neutrons would have to replace protons. Now dear students, if I want neutron excess 8, I don't have to replace 8 protons. You can look into the diagram. I need half of them to be converted. Automatically, if I convert half, in this case it is 4. In this case it is 4. So here you can see that 4, 1, 2, 3, 4, 4 neutrons, 4 protons I mean have got converted into neutrons. So automatically your neutron excess of 1, 2, 3, 4, 5, 6, 7 and 8. Okay. So this is 1, 2, 3, 4, 5, 6, 7, 8. So 8 neutrons have been produced because of conversion of 4 protons into neutrons. So please understand this particular argument. We will use this. Now see, each neutrons would occupy energy levels in energy level by 2 epsilon. So here in this case, I'm talking about this specific case, you can see that this proton has come here, okay, this proton has come here. So basically what has happened is, it was lying here, now it has shifted here at this level. So from this level to this level, this is 2 epsilon. So each proton would increase its energy by 2 epsilon. During this conversion, whichever energy level it was in, now it has got converted into neutron. So it will occupy energy level which is 2 epsilon higher. Now 2 epsilon can also be written as 4 epsilon by 2. I'm deliberately writing as 4 epsilon by 2 because 4 is a number which matches with my number of protons which has got converted. So please understand the argument. Okay. So I'm extending the argument. If this is equal to 8, please understand, then each neutron will increase its energy by 8 epsilon by 2. You can try this by 4. Or if this is equal to 2, let's say, then each nucleon will increase its energy by 2 epsilon by 2, that is epsilon. This is very clear. Okay. So now general case. So general case, each neutron will be increased by energy level half n minus z. Half n minus z is the number of protons which has got converted, multiplied by epsilon by 2. So the total change in energy, this many have converted, multiplied by each one's energy being raised by half n minus z epsilon by 2. So finally I get some expression. N minus z can be written as a minus 2z because a is equal to, that you can write a as n plus z. Okay. So here n can be represented in terms of a, it is a minus z. So a minus z, a minus z, minus z becomes a minus 2z square. Now dear students, I had started off with an assumption that this spacing is equal. No, but as a increases, the spacing will decrease. So delta A, change in energy, will be inversely proportional to A because the spacing decreases as A increases. So I consider this factor also inversely proportional to A, and here proportional to this term A minus 2z square. So I club both of them. So the change in energy now will be epsilon by 8 A minus 2z square upon A constant. I put club all the constant. Now this is a constant, 8 is a constant. Okay, I put all this constant and I call this constant as AA, which is coefficient of asymmetry term. Coefficient, this is coefficient of, remember we had coefficient of volume term. Similarly, surface term, asymmetry. This is coefficient of asymmetry. And please understand this energy, there's a minus sign here because the asymmetry, what do you mean by asymmetry? Asymmetry means the number of protons and number of neutrons are not same. If the number of protons and number of neutrons are not same, if there's an asymmetry, then the binding energy will decrease because the neutrons will be far off than what it was earlier. So there is a minus term here. So this one more term has been introduced to the liquid top model. So now basically this binding energy, I'll take it forward from here. Please pay attention. The total bind, I have introduced 4 terms here. One is the volume term, which I call it as V subscript V. Then second is the surface term, which I call it as B subscript S. Then the third term, which is B coefficient C, and then now fourth term I have introduced, which is capital B, and this is the asymmetric term. So there are 4 terms, 1, 2, 3 and 4, and now we will see whether we are able to reproduce again this graph. We were able to reproduce the graph, but we could not explain the most stable element of the isobar family, one of the problems, and we will try to see this in the next lecture. Will I put all those 4 terms together, and first of all our first job is the shape should be produced, and after that we will test this model against other nuclear phenomena. Right, dear friends? Thank you.